I have been asked to provide an ultra-simple presentation explaining how basic generators operate. Consequently, if you're already expert, there's no need to read this material. It's very important to understand how a transistor works. There are many different types of transistor, but I will describe only one type here, namely an NPN transistor. There are many types of NPN transistor, and while they can have enormously different abilities, they all operate in the same way. Essentially, a transistor is a switch, but while it is a switch which can turn on and off, it can also turn partially on. One major advantage is that a transistor is fast, and it's not unusual for a transistor to switch on and off 3 million times per second. The technically minded people write that as switching speed of 3 MHz, which stands for 3 megahertz, although when I was young it was called 3 million cycles per second, as a cycle is considered to be switching on and off once. The way that a transistor works is not difficult to understand. It has two current flow paths inside it. One is for low currents and one is for high currents. The low current path controls the current flow through the high current path. You can think of it like this. The diagram here shows the notion of how a transistor actually works. The high current path flows from the collector through to the emitter. The low current path, which controls the high current path, flows from the base through to the emitter. And that's the way that an NPN transistor works. The low current path is between the base and emitter, and while the high current path between the collector and emitter is marked as R for resistor, strictly speaking it is a resistor, and one which can change its value from perhaps 1 million ohms to 1/10 of an ohm. Remember that it can perform that change in resistance in less than 1/millionth of a second. The size and power rating of the resistor R dictates the power of the transistor. Some transistors can only handle 1/10 of an amp, while others can handle 10 amps. Some can handle only 20 volts, while some powerful transistors can handle 1000 volts. Transistors are heat sensitive, so if you're soldering them in place, you need to be quick, and if possible, use a heat shunt like a pair of pliers to keep the heat of the joint away from the transistor. It's important to understand the low current path from base to emitter. Because of the material from which the transistor is made, that path does not conduct current until the voltage at the base is higher than the voltage at the emitter. What that exact voltage difference needs to be depends on the particular transistor, but 0.65 volts is a typical value. A common way of connecting NPN transistors is like this. You have a power supply, which is shown as a battery here, giving 12 volts and 0 volts. The 12 volts runs through a load, which is in actual fact a light bulb, down through the collector and the high current path through to the emitter and back to the battery. The base voltage is provided by an ordinary resistor. That resistor has 12 volts at one side and 0.65 volts on the other side, and you choose the size and value of the resistor to deal with the current that will flow into the base and out of the emitter. In this circuit, the light bulb is the load, and so that's what we wish to switch on and off when it suits us to do so. The voltage at the base, as I say, is supplied through the resistor R, and the voltage across that resistor is 12 volts minus 0.6 volts, which is 11.35 volts. Technically minded people call this kind of circuit a common emitter circuit because the transistor emitter is connected to the 0-volt line. Transistors are supplied in various packages. A common powerful 12 amp 700 volt transistor is the MJE 13009, which looks like this. That's the way that it's packaged. It's got 3 pins coming out of it: base, collector and emitter, and it is a common packaging method to put it like that. Transistors of that sort of level of power have a metal tag, shown here, which allows the transistor to be bolted to a heat sink, which can carry away excess heat generated by the large current flowing through the transistor. It is a good idea to always use a heat sink. They come in many different shapes and sizes, and a good one might look like this here. It has a flat area which the metal tab of the transistor can be bolted to, and then there are a lot of dark colored fins which can radiate away heat. This particular one has got 2 metal shafts sticking out of it, which can be pressed through holes in a circuit board and soldered to give a strong support for the particular heatsink itself and the transistor which is bolted to it. Another very important component is a coil of wire. Winding a coil of wire is very easy. It's an easy thing to do, and even a child can manage it quite easily. Essentially, it's just turns of wire placed around a former, such as a cardboard tube. A simple one wound on a plastic tube and wrapped in white tape looks like this. That particular coil was wound by Alex Core. Surprisingly, a coil happens to be one of the most complicated and useful devices which we know about. The characteristics of a coil can be changed quite easily, as the coil diameter, the coil length, the wire thickness, the number of turns, the spacing between the turns, and the method of connection makes a great difference. The really nice thing about a coil is that it can be used to draw in extra energy from the local environment. If you connect a coil across a 12-volt battery, then current flows through the coil. How much current? The thicker the wire, the fewer the turns, the greater the current will be, and the faster it happens. The really interesting thing is that if you break the connection and stop supplying current to the coil, then a voltage is generated across the ends of the coil, and that voltage will be much higher than the original 12 volts. This picture shows how much voltage is generated by applying 12 volts to the coil shown above. There's the coil, and a small simple circuit is used to supply 12 volts to it. The output is taken through a diode to a capacitor, and the voltmeter is measuring the voltage developed across the capacitor, as that shows approximately how high the voltage pulses entering the capacitor are. And you can see from this very clear picture here that in this instance 214 volts is being developed on the capacitor as a result of the pulses from a 12-volt supply. As you can see, the coil generates 214 volts when switched on and off by a transistor. A high voltage like that can be very useful. For example, it could be used to charge a row of 10 12-volt batteries if they're connected in a chain. Connected in a chain, they will make 120 volts, and 214 volts can most definitely charge a 120 volt battery. When connected in that way, the same charging current flows through each battery, and they all get charged at the same rate. That's something that's not immediately obvious to many people, but when you connect batteries in series like that and apply a voltage to the series group, the current flows through all of the batteries from the plus of the supply to the minus of the supply voltage, and the current flowing through the batteries is always the same for each battery. Another interesting fact about a coil is that when a current flows through it, it generates a magnetic field. That magnetic field switches on and off with the current flow. A developer in South Africa uses that magnetic field to keep a rotor spinning continuously. He's built several different versions of his rotor system. The one shown here uses 10 small coils and gives a continuous output of 150 watts of electricity at mains voltage and mains frequency. He started by making a 110 millimeter diameter rotor out of acrylic plastic. It's very clear acrylic plastic, so it's quite difficult to see in this picture. The disc then has got 5 evenly spaced holes drilled into it, and inside each hole are placed 9 3 millimeter thick 20 millimeter diameter ferrite magnets. The disc itself then is surrounded by the strip of white plastic here, which has been cut from a plastic pipe, and that makes sure that none of the magnets can ever fly free of the disc itself. The disc then is mounted on an old computer hard disk drive bearing. It looks like this. There's the disc itself surrounded by the strip of plastic cut from a pipe. There is the bearing itself, and this is just a mounting stand which holds the thing in position so it can rotate freely. A ring of 10 small coils is then mounted around the rotor disc. The coils are small, they're very neatly wound because the guy doing it is very accurate in his construction. The stand there supports the set of 10 coils. Each of the 10 coils is wound with 22 meters of wire. The wire is 0.711 millimeters in diameter. It's solid enameled copper wire, which is easily available, and the winding covers a 24 millimeter length of the central cast iron core. The cast iron core is a 6 millimeter cast iron bolt which has been plated with a zinc coating. The plastic flanges, these are the white plastic flanges here at each end of the coil, which keeps the wire in position. They're 30 millimeters in diameter, and the coils are connected as 2 sets of 5 coils each set of coils having an overall DC resistance of about 4 ohms. The switching on and off of the coils is synchronized by a magnetic sensor which detects the rotor magnets passing by it. The sensor is mounted just outside the rotor disc, and the wires from it are taken away to circuitry. The mounting that has been used here allows slight adjustment sideways and vertically, and that makes a difference as to exactly when the magnetic sensor switches on and off. The circuit using the disc and the sensor emitting the circuitry that pulses the actual transistor is like this. You've got a set of coils here. 5 coils are shown connected in blue and 5 coils are shown connected in red, and the 2 sets of coils are powered by the battery, which is a 12 volt 7 amp hour battery, which passes through the coils and out to the transistor itself. Transistor is a slightly different type. It's an IRF 840. It's a field effect transistor, or commonly called a FET, and the sets of coils are powered when that transistor switches on. The FET transistor is very much like an NPN transistor in the way that it operates. The load shown here can be a 12-volt inverter available for powering small mains voltage equipment. If you are not aware how this circuit actually operates, then you could easily think that the 12-volt battery is just powering the inverter. That's not actually the case. The battery can definitely run the output inverter for a little while, but it could certainly not run it indefinitely. In actual fact, the battery has been used as a passive device in this particular circuit. It's there to hold down the voltage supplied to the inverter down to 12 volts. If the battery were not there, then the high voltage spikes, which are fed to the battery from the transistor itself, would damage the inverter. The FET transistor is very much like an NPN transistor. The gate, which controls it, is like the base. The drain, which handles the large heavy-duty current, is the equivalent of the collector, and the source, S, is the equivalent of the emitter on an NPN transistor. We have not mentioned the circuitry which produces the synchronized pulses to the transistor. That circuitry is shown here. You have two sensors because you're using two separate sets of 5 coils. The two sensors, though they don't look it, are actually wired exactly across each other. The positive line comes in here on this one and then down across to the same connection on the second sensor. The central connection wires of the sensors are connected directly to the minus, so the sensors are both connected directly across the plus and the minus of the battery, and when the magnet passes by, the resistance of the sensors changes from very high to very low. That effectively connects the plus line of the battery through a 1K resistor to the base of this particular transistor. This transistor has been chosen to be a C5353 type, which you can get quite readily. The transistor itself forms a voltage divider pair between the plus and the minus line, so the voltage at the collector will be very high when the transistor is switched off and very low when the transistor is switched on. When the transistor switches on, the voltage on the collector drops very low, and it's connected through this 100 ohm resistor to the gate of the main switching transistor. That effectively turns this transistor off. The IRF 840 turns off when the C5353 turns on. Similarly, when the magnet passes by the sensor goes to a high resistance, and the C5353 transistor is effectively starved of current and switches off, which pushes the voltage of the collector high, which feeds through the 100 ohm resistor and switches the IRF 840 field effect transistor solidly on. The generator is started by the user giving the rotor a spin, and that causes the magnets to pass by the sensors, and that causes the IRF 840 transistor to keep switching on and off, and that in turn causes current flow through the coils to keep switching on and off, feeding excess power back to the battery. The excess power is fed through 3 amp fast acting diodes, which are ultra fast 5408 diodes. They're powerful diodes and very fast operating. The coils, when they get switched off, generate this large voltage pulse across the coil, and that produces a short-lived, very large magnetic field, and that magnetic field occurs just after the magnet passes the core of the coil. That creates a major push on the rotor magnet, and that keeps the rotor spinning. Even though there's no motor as such, the rotor continuously spins. The spinning rotor does create a slight sound, and if that's considered a nuisance, then some simple soundproofing can drop the sound level to near zero. The output of this particular generator is excellent, but inevitably people want to know how to increase the output. For example, suppose you've made two identical generators like this, each of them putting out 150 watts of alternating current electricity. You can't just connect them together to double the output and be sure that it will work, because they're not synchronized, and one output may be going high while the other output is going low. So to overcome that problem, instead of doing that, you join the two direct current outputs together and then connect a larger inverter to that combined DC output. And an alternative to doing this is to use this particular circuit, or a motionless circuit, to charge a bank of batteries. Those charged batteries can then be used to power a larger inverter to provide power to larger items of household equipment, admittedly not on a continuous basis, but for shorter periods of time. This has a major advantage in that pulse charged batteries have a very much enhanced working life, and if used on a daily basis they can develop increased working capacity. In other words, the batteries look as if they're bigger than they actually are. If you're concerned about the short working life of a lead acid battery, which is typically about 1,000 cycles, that's the 1,000 times it can be charged and discharged, then when the battery reaches the end of its working life and will no longer hold a charge, the battery acid can be flushed out and the acid replaced with alum, which works very well indeed. If you wish to avoid having to make an accurate rotor, then a very efficient motionless battery charger can be made from the circuit which has been shared by Alex Core. It is based on the famous Joule thief circuit, and it's very simple. The Joule thief circuit generates its own oscillations by making a coil part of a frequency feedback circuit, like this. This is a Joule thief circuit. There are two windings which are positioned together. In fact, the two windings are shown here in this diagram, one in red and one in blue. The two windings are connected together, but notice the dots. These dots indicate the start of the particular winding. So the red wire is wound round side by side with the blue wire down the length of a tube or former. At the end of this, the end of the blue wire is connected back to the start of the red wire. Those two wires joined together are then connected to the plus of the battery. The end of the red wire is then connected directly to the collector. The other end of the blue wire is connected through a 1K resistor to the base of an NPN transistor, this one being a 2N2222 transistor, which is a small unit with a high gain and can handle about 0.8 watts. The original objective for this circuit was to power a light emitting diode using a dry cell battery which had already been discharged past its working voltage. The Joule thief circuit works very well indeed. The dots on the coil windings indicate the start of each coil, so the end of one winding is connected to the start of the other winding, and the join is connected to the plus of the battery. When the battery is connected to the circuit, current flows down the left hand coil through the 1K resistor into the base of the transistor and switches it on. As it switches on, the collector voltage drops down to 0 volts and you get the full battery voltage across the second coil. That only lasts for a short period of time, but it induces, through its closeness to the first coil, a pulse in the first coil. And that extra pulse in the first coil is fed through the 1K resistor into the base of the transistor and switches it on, which powers the second coil, which induces a current in the first coil, which flows through the 1K resistor into the base of the transistor and switches it on. That generates a considerably higher voltage at the collector than is given by the battery. The battery voltage can be as low as, say, 0.2 volts, but you could get typically, say, 11 volts coming off the collector. That 11 volts is pulled down by the LED, typically to its operating voltage, which is generally about 3 volts. Depends on the particular LED. But that's a very effective dual-T circuit, which originally was intended just to light an LED using what is effectively a dead and discharged dry battery. The system itself operates about 250,000 times a second, and the pulses generated are far greater than the battery's voltage. The coil is effectively very simple to wind. You wind it from 2 strands of wire. It doesn't have to be very long or great. But a stream of high voltage pulses like that can be used for more useful things, like recharging powerful batteries. Alex Core shows how in this particular circuit diagram. He has a dual-T circuit. There are the 2 coils wound, and he's done 100 turns of 0.5 millimeter enamel copper wire round a former. Typically it's probably the white taped former shown in the earlier pictures, but those are connected to the collector of the transistor and through a resistor to the base of the transistor, and the output high voltage spikes are fed through a UF 5408 high speed 3 amp diode through to a row of 4 batteries which are connected to the plus of the drive battery. The drive battery powers the circuit. He has a 2700 picofarad small capacitor, ceramic capacitor, connected across the resistor. Ostensibly, we'll say for the moment that is to adjust the frequency of the transistor. It's slightly more subtle than that, but we're not going to go into that just here. The voltage on the battery driving the circuit is marked at V. If V is 12 volts, then the resistor R will be a 1K resistor. If V is 24 volts, then the R will be 2K resistor. With 36 volts, it's 3K resistor, and so on. So there's a 1K for every 12 volts in the drive battery. The drive battery can be as big as your transistor will manage. This particular transistor he's chosen is a 2SC3552 transistor. That's a very powerful transistor indeed. It can handle anything from 500 to 1100 volts. It carries 12 amps continuously. It can dissipate 150 watts, provided obviously it has a heatsink, and it's also very fast acting. It's a very well liked professional transistor. That is, a transistor which is favored by professional designers for manufacturers. The circuit that he's using is still essentially a dual-T circuit, which is using this very powerful transistor, a 3 amp fast acting diode, and it uses the pulses generated to charge 4 batteries connected in a string. A single battery is used to run the circuit and charge the 4 batteries. In actual fact, it charges 5 batteries because the charging current flows on through the battery driving the circuit. It's not enough to keep the battery driving the circuit fully charged, so the battery driving the circuit will actually run down, but it will charge 4 bigger batteries fully before it does run down. Again, it's the same dual-T circuit, 2 100 turn, 2 cores, 2 strands of wire, each with 100 turns side by side, wound round an air core former. By air core, that just means it doesn't have anything in it. It's an empty tube that's been used to wrap the turns of wire around. Again, he has a 2700 picofarad ceramic capacitor connected across the resistor R, feeding the transistor. He does show a similar 2700 picofarad across the resistor feeding current to the second transistor, though he does say that it's not necessary to do it. You can have it or you don't have to have it, because the first one will operate satisfactorily for all of the transistors in the circuit. You can have up to 10 additional transistor circuits going along this string of circuitry, and you notice that the first transistor feeds its output through a red wire to the plus of the string of batteries. The second one also feeds its plus through a separate wire to the plus of the batteries, and each of the additional stages has a separate wire going to the plus of the batteries. You may say, oh well, you could just connect the wires together. Well, yes you could, but it won't work as well. Those separate wires are important for a multiple charging stage like this. Again, the wire used for winding these coils is solid enamel copper wire with a diameter of about 1/2 millimeter. It can be just under or slightly over 1/2 millimeter. If you use other diameters of wire, you get a very different result in the circuit, but I suggest that you don't bother experimenting with things like that. Go with this circuit, which works very well, using 1/2 millimeter diameter wire in the coils. I personally suspect that a lot more than 4 batteries could be charged at the same time using this circuit. Although the batteries are charged in a chain, they will normally be connected in parallel when being used to power household equipment. When you use them connected in parallel like this, the amount of current drawn by the inverter to power the household equipment, be it a television or a washing machine or whatever, is divided between the batteries. The batteries are connected together to form a larger capacity battery, and that lets the system operate reliably for a longer period of time. But that is basically the way that simple circuits operate, and I apologize for being so painstakingly simple in describing it in this way.